Hello and welcome to the Conversation Weekly.
This week, we're talking about nuclear fusion. In early February, a lab in the UK produced the most energy ever in a controlled fusion reaction. We asked two experts what this means and how long it'll take before we can turn these experiments into actual nuclear fusion power plants.
The first generation of fusion reactors can be in the 60s or in the 70s.
So what we are trying to reproduce here on our planet is what makes energy in the stars.
And later in the show, I talked to a social psychologist about new research into the societal pressure some people feel to be happy.
When a lot of people seem to be doing well and happy, it can actually exacerbate those feelings of low mood.
I'm Dan Marino in San Francisco.
And I'm Gemma Ware in London. You're listening to the Conversation Weekly, the world explained by experts. Scientists first managed to demonstrate the ability to fuse two atoms together in lab experiments back in the 1930s.
Nuclear science has come a very long way since then, and every few months you'll see headlines proclaiming the next breakthrough in nuclear fusion.
And yet, we still haven't managed to harness the energy produced by nuclear fusion to actually make electricity.
In early February, scientists at the Joint European Torus Lab in Oxfordshire, in the UK, announced they'd broken the world record for the amount of energy produced in a controlled nuclear fusion experiment.
The key part of this reaction only lasts for 5 seconds and only generated enough power for 60 kettles, but it is an important proof of the principles of fusion.
JET, which is run by the UK Atomic Energy Agency, was built in the 1980s and is currently the world's largest fusion reactor. And this is what it sounded like when scientists there broke that world record.
So how excited should we really be about this news? How much closer does breaking a world record take us to actually getting a nuclear fusion power plant? And what would the success of that really mean for future energy needs? To find the answers to these questions, I've been speaking to a couple of scientists, one in the US and one in Spain, who spent their careers trying to make nuclear fusion power plants a reality.
My name is Livia Casali, and I'm professor at the University of Tennessee, Knoxville, in the Department of Nuclear Engineering. I'm a nuclear physicist, and I work in nuclear fusion research.
Wonderful. So there's been some big fusion news the last couple weeks. Can you explain what just happened at the Joint European Torus experiment? This is the JET experiment.
Yes, so JET set the world record for the most energy produced in a single fusion shot, so 59 megajoules of heat. And this is very important because these results confirm that we can achieve a fusion energy using deuterium and tritium fuel mix, which is the same fuel mix that we are planning to use for future fusion devices.
Okay, nuclear physics is complicated. So throughout this episode, we're going to be breaking things down to help make sure we all understand what's going on here. So I'll let Livia get us started.
We refer to fusion as the process in which atomic nuclei of low atomic number fuse to form a heavier nucleus with the release of really an incredible amount of energy.
The nucleus is the thing at the center of every atom, and it makes up pretty much all the mass of an atom. Not all atoms are the same weight, though. Oxygen, for example, is heavier than helium. This is why balloons float, so their nuclei are different weights. The light nuclei that Livia is referring to mean they're lighter elements, and the lightest of all is the gas hydrogen. So it's very difficult to fuse two nuclei together.
We need to have high enough plasma densities and temperature for a sufficient time. Now, this is needed because the nuclei need to collide with each other. And this has to happen at very high temperature because they need to overcome their mutual electrical repulsion, and only then they can fuse together. And so for this to happen, we need to confine the nuclei in order to increase the chances of collisions.
This is the opposite of fission. Fission is how we power today's nuclear power plants and require much heavier atoms like uranium, which has 235 protons compared to hydrogen's single proton.
In fission, we split a big nucleus in smaller ones, and these produce energy. Whereas in fusion, we fuse the two small atoms into a big one, and these produce even more energy than fission.
So where does this energy come from? Well, the thing with fusion is that the end product you get is actually lighter than the two nuclei you smush together. And this is where Einstein, of course, comes into play, with his famous equation E equals mc squared. That's energy equals mass times the speed of light squared.
So the Einstein equation tells us this extra mass isn't lost, but is converted into energy. And that's why we get so much energy out of making the fusion of these light nuclei.
So if you lose mass during a fusion equation, that mass doesn't simply wink out of existence, it gets released as energy. And theoretically, this energy is what would power fusion power plants. So there is one place right nearby where fusion happens all the time.
And that's our sun. So what we are trying to reproduce here on our planet is what makes energy in the stars.
The sun is made up of plasma. These are atoms that have been stripped of their electrons and are super hot and superconductive. And importantly, plasma is electromagnetic, so it responds to electromagnetism.
There is a big difference when we consider the stars, and is that in the stars, the plasma is confined by its own gravity. However, here on our planet, we don't have enough gravity to confine the plasmas. And so one of the ways that we can actually confine the plasma is utilizing powerful magnetic field.
This type of fusion that uses magnets is called magnetic confinement. There's a couple other ways you can drive fusion. One uses lasers to crush atoms together. You can even use bombs. That's actually how thermonuclear warheads are made. But we're going to be focusing on magnetic confinement. That's what the JET experiment in the UK used to get its recent and really impressive result. The magnetic confinement approach uses magnetic fields to do all sorts of stuff to control the plasma and the fusion inside of the vacuum, and importantly, to keep the hot plasma from touching the walls and basically melting everything. All this happens inside of a special kind of container called a tokamak.
So the term tokamak comes from the Russian word, which stands for toroidal chamber with magnetic coils. Practically, this torus is a donut shape, and our plasma is in there. So we first need to create this plasma, and what we do is that we induce an electric current, pass through the vessel, and then the plasma starts to form. And then the energized plasma particle will collide, heat up, and we will use auxiliary heating system to increase the temperature to the required level for the fusion reactions to occur.
So what is the actual fuel used for fusion reactions? On Earth at least, most fusion processes use hydrogen isotopes. Isotopes are just different versions of an element that have a different number of neutrons in the nucleus. The main fuels used in the JET experiment are deuterium and tritium, two isotopes of hydrogen. For decades, scientists have been able to do nuclear fusion with these isotopes. But sustaining it is the tricky part of a fusion reaction. So if you remember at the beginning of this episode, Livia told me that the JET experiment broke the world record for the most amount of fusion energy produced in a single attempt, or a single shot. This shot lasted for 5 seconds, and it produced 59 megajoules of heat.
JET already actually set a world record back in 1997. However, the difference is that back then JET had a carbon wall. And this carbon wall was acting as a sponge, so to say, for the hydrogen isotope which create our plasma. And so what enabled now this new record was really the transition, a big technology change in the wall material from the carbon wall to a tungsten and beryllium wall.
The wall materials are just the materials that line the inside of the vacuum container inside the tokamak.
The issues that the fusion community faced with the transition from the carbon wall to the tungsten wall was that the performance were actually different compared to the carbon wall. And so here the fusion community really worked hard to understand what these differences were and try to recover performance. And so this is why these results are so important, because they can confirm that we can achieve high power operation compatible with the wall material that is planned for future reactors.
JET uses the same setup, more or less, as the world's future biggest tokamak, called ITER. ITER is currently being built in the south of France near Marseille. It's due to begin operations in 2026.
ITER, which in Latin means the way, is really the most complex experiment ever built and really ever conceived in humanity. And this is not only from the physics or the technology point of view, but also in a sense from a political point of view, because 35 nations are working together to really make this dream of energy independence possible.
So how is ITER different than JET?
So ITER, just to start with, is much, much bigger.
How big are we talking here?
So the major radius of ITER will be 6.2 meters. And in comparison, JET is 2.96. Also, another important comparison is about the plasma volume, which in ITER will be around 830 cubic meters, whereas in JET is around 100 cubic meters.
And how big is the vessel in tokamak in ITER?
Is really big. The entire building where the tokamak is going to be as tall as the Arc of Triomphe in Paris.
Okay, so that's huge. What is ITER meant to demonstrate here, Livia?
So ITER is supposed to demonstrate the feasibility of fusion energy as energy source. So we are expecting that ITER will produce 10 times higher energy, so in output compared to the energy we put in, the power we put in.
What do you call this ratio of energy in to energy out? Is there a name for it?
Yeah, we call it Q. So a Q equal 1 is the condition for what we call break even. So we get out whatever we put in. But in ITER, we are expecting to see a 10 times as much energy as we put in. So a Q equal 10.
So JET was only able to run for about 5 seconds, but to actually make a real power plant, you need to be able to run a fusion process for much longer. So can you explain that, Livia?
Yes. So, 5 seconds is actually an important number. One of the reasons was only 5 seconds is because JET has copper coils. In ITER, the situation will be different because we will have superconductive magnets. And this will allow to have this fusion sustained for much longer time. In fact, the progress in the manufacturing capabilities for superconductive magnets is really one of the big players for the advancement of fusion as an energy source.
So JET could have produced more energy, but it would have melted the copper coils or something?
Yeah, exactly. The copper coils would just get too hot.
A lot of this stuff seems like an engineering question, right? It's not like the physics is this mysterious thing and you need another Einstein to come out and discover some new equations. How would you consider this concept of physics versus engineering in fusion right now? Where do we need to improve more?
Well, there are still a lot of issues. We need to understand the physics behind, as you mentioned, is complex and difficult. There are still unknowns yet to be uncovered and understood. But we have made great strides in the understanding of the plasma physics over the past decades. When we talk about fusion power plants, I would say that the question is more about how to achieve the conditions, not what the conditions are. We know that. We know how to make a fusion. One of the big challenges that remains and to overcome is really the handling of the power which flows out of the plasma.
Fusion at this point is really as much an engineering problem as it is anything else. If you want to fix the engineering problems of fusion, you have to do bigger and you have to do more complex experiments. You have to try out new materials. You have to test how these materials will react in the new setups and, importantly, under hot temperatures. And you have to put all this into a machine that will not just fuse nuclei, but actually produce energy and produce electricity.
To make a fusion reaction is very easy, and we have made a lot of fusion reactions. But of course, that does not mean that we are able to produce energy.
This is Angel Ibarra. Angel is a researcher at CIEMAT, the Center for Energy, Environmental, and Technological Research in Madrid. This is Spain's national fusion laboratory. He's been working on fusion for more than 35 years. Currently, he's leading a consortium that's building a facility in Granada to test the materials needed for the inside of nuclear fusion reactors. I asked him what the roadmap looks like from where we are today. How does the world get from the 5 seconds of jet to a fully functioning nuclear fusion power plant that can produce energy? And Angel said that the ITER experiment Livia was telling me about in southern France is a crucial next step.
The important thing of ITER is that it will demonstrate that we are able to control the complete fusion process, and we are able to maintain it during long period of time, not just 5 seconds like the result of jet, but during a period of time of 15 minutes, half an hour or something like this. So if we are able to do this, that means that we will be able to do this for 2 hours or 1 day or things like this.
ITER won't be producing electricity. Its job is to demonstrate that the modern materials and designs of a fusion reactor can withstand the huge temperatures and basically just not melt over a long period of time. But turning the proof of concept of ITER into electricity is the important next step. So how does that happen?
The way in which we will produce electricity using a fusion reactor is that we have the fusion reaction in which some neutrons are produced.
One of the byproducts of a fusion reaction are lots of neutrons that are traveling really fast. To capture the kinetic energy of these fast-moving neutrons, engineers are planning to coat the inside of the walls of the vacuum chamber with a kind of blanket that can convert kinetic energy into heat.
And then we put water there or some other coolant, and then we take this coolant to a turbine, and then we are able to produce electricity.
Yeah, we're still using the steam engine, right?
That's right. It is exactly the same principle than in a carbon or gas or many of other energy sources. The point is that to be able to be efficient on this, you need that this coolant is at high temperature, 400, 500, 600 degrees centigrade. And this requires that all the materials and the components in this area are working properly at these temperatures. At this moment, we do not have the materials, or we are not enough sure that the materials will work properly in these temperatures.
Angel says that ITER isn't being designed to withstand temperatures quite this high, more like 100, 150 degrees centigrade in this case. And that's one of the reasons why it won't be able to produce electricity. It's not really hot enough to produce a ton of steam. So the next step after ITER is to build a demonstration reactor that will, well, actually generate power. We're talking a real fusion power plant here.
The characteristics of these demonstration reactors are slightly different in each country. Europe has a slightly different approach than Japan or than Russia, but at the end it's more or less the same. It will be a machine that will be able to produce electricity in one way or another, with a net gain of energy, if you want, and with a complete fuel cycle.
Angel says that there will be just 2 or 3 of these in the world. For example, Europe's government-funded Eurofusion project is planning a demonstration plant called, aptly, Demo.
The ideas that we have in Europe today is that this demo reactor can be available around the 50s, in 2050 or something like this. And then the first generation of fusion reactors can be in the 60s or in the 70s. It cannot be, or it probably will not be much faster than this.
China, Russia, Japan, South Korea, and India are all also working on designs for demo plants. These demonstration plants will generate different amounts of electricity depending on their size and design, but the goal is all the same: to show that you can create a fusion reaction that releases more energy than you put into it, and that you can turn the energy into electricity.
The power is not a problem, really. I mean, we can design the machine to a wide range of powers. The demo machine that is being designed in Europe today, I think it is a 500 megawatts machine, more or less. But the design can be easily modified to be 1,000 or even 2,000 megawatts of power.
Like ITER and the jet experiment that just broke the fusion power record, many of these demo plants are likely to use deuterium and tritium as their fusion fuel source. And fuel, especially in the age of climate change, is an important thing to consider. So where do these hydrogen isotopes come from?
Deuterium is very easy because you have deuterium in the water. we can take out from the seawater without any problem, or from normal water. And we know the procedure to get it out. So deuterium is not an issue. It is more difficult with tritium. Tritium is a radioactive isotope, and with a decay time of around 12 years.
Decay time is another word for the half-life, which you've probably heard of. What this means is that if you had 100 grams of tritium, half of it would have decayed by irradiating off some of its particles, and only 50 grams would be left.
There is not too much tritium available in the Earth. There is some tens of kilograms of tritium, but we will need around this amount of tritium, a few kilograms in each fusion reactor.
That sounds like a problem, but here's a pretty beautiful solution. It's actually possible to make tritium inside a fusion reactor. To do this, you use another element, lithium. Lithium is way more available in the world. It can also be potentially just extracted from seawater. So let's dive back inside our donut-shaped tokamak for a second here. To make tritium, you basically just put some lithium inside the lining of the wall that contains the hot plasma.
And then the neutrons coming from the fusion has a nuclear reaction with the lithium, and this reaction produces tritium atom, and then we take this tritium atom and we use as a fuel that is always available.
Some experiments have already tested this method of breeding tritium as fuel, but the full cycle will only be really tested once a fusion demo reactor is built. Alright, so we're talking about nuclear stuff, and we have to talk about radioactive waste. Nuclear fission, this is today's nuclear power plants, produce a ton of radioactive waste with decay times in the hundreds and thousands and tens of thousands of years. And the world is still trying to figure out what to do with all this radioactive waste. Angel says this is much less of a problem with nuclear fusion.
In the case of a fusion reaction, the output of the reaction, you have deuterium and tritium, they react together, and then they produce helium that is not radioactive. The possible problem is that we have neutrons, and the neutrons go to the walls of the vacuum vessel, and then they interact with the materials, and there are some nuclear reactions that give rise to some radioactive materials. So in a fusion reactor, there is a radioactive inventory that is significant, that is important, but they will decay in a relatively short time. And that means that the waste management issue of a fusion reactor is much simpler than the waste management in a fission reactor.
Another advantage over today's fission plants is that you can't have a meltdown like Chernobyl or Fukushima.
One of the key things of a fusion reactor from the safety point of view is that we say that there is no significant risk because it is not possible to have a chain reaction. Anything stops the fusion reaction. But of course that means also that it is very easy to stop the fusion reactor, and then to assure that the reactor is working during long periods of time will be a significant engineering challenge.
So if these engineering challenges can be overcome, what does the advent of nuclear fusion actually mean for the planet? Fusion is often held up as a holy grail of sorts of free, clean, and potentially sort of limitless energy. But Angel says it's not quite right to call it a renewable energy source.
Strictly speaking, the word renewable means that you are using a fuel that is always available. So you are not spending anything, I would say. From this point of view, fusion is not renewable because you are using deuterium and lithium, and they are materials that they are in the earth, but in a few thousand years they will disappear.
To be fair, I kind of think that's splitting hairs a bit, because the important thing is nuclear fusion doesn't produce CO2 like burning coal or natural gas or oil. Its main byproduct is helium, stuff that makes balloons float and your voice go high.
In principle, this is a big advantage from the climate change point of view.
But Angel's a bit wary of considering fusion a cure for climate change, as it were.
To think that the energy production in the future will be based in a single type of energy sources is not feasible, it's not realistic. At the end, we need to have a range of different ways to produce energy. So the way in which I see the energy mix in the future should be a mix of solar energy, wind energy, and hopefully fusion energy. And the mix of these three ones will be a sustainable way of producing energy.
Looking even further ahead, Angel sees fusion as an important source to help fill gaps and meet an ever-growing need for energy.
It is true that we are now making, or in theory, we should make a big effort to change the way in which we are producing energy in the world. We need to move to other type of energy to reduce the climate change effects. But we must be aware that the progress of the humanity requires always more energy. And just making very rough numbers, it is very clear that 100 years from now, we will need to produce 2, 3, 4 times more energy than today, using completely different methods to the one that we are using today. So that means that maybe in 2050, fusion cannot have a significant impact on the energy production, but 100 years from now, fusion should have a significant impact.
It's good to hear from both Livia and Angel that nuclear fusion is now an engineering problem rather than a theoretical physics one.
Totally. And the fun thing about engineering problems is that you can solve them with money and experiments. Most of the investment in nuclear fusion up till now has been by governments. But Livia said that a lot of private money is beginning to flow into the sector. According to Forbes, 2021 saw $3 billion of private investment in nuclear fusion startups. Many of these companies are taking different routes to achieve nuclear fusion, not the magnetic nuclear fusion we've been talking about, but it's clear momentum is building.
So Dan, after these conversations, after your calls with Livia and Angel, do you think we'll get nuclear fusion in my lifetime, your lifetime?
Yeah, I think if I live long enough, there's a decent chance we will see nuclear fusion power in our lifetimes.
For our next story, we're talking about happiness. Every year, the World Happiness Report rates the level of happiness around the world in an index. In the most recent one, based on surveys from 2020, Finland came top, followed by Iceland and then Denmark.
It's always those northern European countries that sound like the place to be for some reason.
Yeah, they do, don't they? But some new research has actually found that living in a country that does well on these happiness indices can actually lead to greater social pressure to feel happy. And for some people, this pressure can actually make them feel unhappy. To find out more, I called up one of the Australian psychologists who was involved in the new study.
So I'm Bastian, professor at the University of Melbourne, director of the Ethics and Wellbeing Research Hub in the School of Psychological Sciences there. And my research broadly focuses on the issues of ethical decision-making and behaviour, but also well-being, happiness.
And how did you get into studying this happiness question?
Well, I was particularly interested in the positive psychology movement and understanding, I suppose, how that has focused people on happiness in some ways, which has been very important, but also the idea that this has led sometimes to a bit of pressure for people, perhaps, where when we do focus on happiness or the importance of it, that it tends to have this funny, ironic kind of effect of backfiring on us. I think one of the channels that it comes through is probably through advertising. So advertisers often pair happy faces with the products they're advertising. I think that, certainly our ability to portray ourselves on social media has given us that capacity to choose how we do that and to be portrayed more broadly and to have that reach. And of course, the way that we do that tends to be positive. We tend to share our positive experiences, our successes. And so, it's very easy to think that other people on social media are all experiencing this sort of emotional content or experience all the time compared to perhaps how we do.
And you've just published a new study looking into this societal pressure. What was the main question you were trying to answer when you set out doing this study?
Well, we've been looking at this for a number of years and have published a number of papers looking at this, what we call social expectancies. This is the idea that I feel that people around me have a certain expectation of my emotional life to keep up the positive emotion, to minimise the negative emotion. And we've certainly found that sort of social pressure or that perceived expectation seems to have negative wellbeing consequences for people.
Such as what?
For example, it certainly leads to more negative emotionality, less positive emotionality, less satisfaction with life, more depression, more anxiety, feelings of loneliness. And so we have found that it has those negative implications, although our studies have mostly focused on Australia or sometimes the UK and America. So we were interested to see, well, does this replicate across a large number of countries? So we collected data from 40 countries in this large multinational survey. And the first initial finding was a very resounding yes. There's certainly, to the extent that people do experience this social pressure, it tends to have a negative implication for their well-being. And that's true across all 40 countries.
Were the 40 countries that you surveyed, were they generally quite rich countries or were they a spectrum?
So we didn't put GDP in, but we had countries in there right across the world, through Asia, through Africa, through to Western, Eastern Europe, America, Australia. So we did sample quite broadly.
So these 40 countries were all over the world, and this confirmed the finding that you'd already found?
That's right. Then we went a little bit further, and what we can do when we've got 40 countries is we can also get country-level data. So we looked at the World Happiness Index of how happy countries were ranked, and we then looked at that relationship between that sort of perceived social pressure that people have and their well-being outcomes. And we found that it was actually stronger in countries that ranked more highly on the World Happiness Index. So it would seem that, whilst on average countries and people in those countries are reporting high levels of happiness, for some, that actually leads to a greater sense of social pressure and can actually lead to poorer and negative well-being outcomes.
Just explain a little bit, if you could, how the World Happiness Index is put together. What is it trying to measure?
I mean, people tended to look at societal well-being very much as a sort of GDP factor. So countries that had high levels of economic resource were viewed as having high levels of, I suppose, the capacity to provide for people's needs. But more recently, we've moved to looking at those sort of more subjective factors where people indicate, how satisfied are they with their lives. So those sort of subjective measures are the sorts of things that feed into the World Happiness Index. So it's that subjective indicator of, how much a country is flourishing in that sense, just in the same way that a GDP indicates how much a country is flourishing economically.
So what you found is a relationship, a correlation between a country's place on the World Happiness Index and the pressure some people say they feel to be happy.
Yes, that was what we found, that focusing on the World Happiness Index at the country level did predict a change in that relationship between the felt social pressure to maintain happiness and avoid negative emotion and those negative well-being outcomes. So it was in happier countries that we found that a relationship more strongly. Yeah.
And is there an example of the kind of countries we're talking about here?
Probably a common example that people point to is Denmark, because Denmark often ranks most highly in terms of happiness. It's a very egalitarian society, it does tend to have reasonably high levels of GDP as well. But say, for example, in a country like Denmark, though, that relationship between the felt social pressure to, maintain happiness and not to experience emotions like depression, anxiety, that sort of sense of keeping up with the Joneses, I suppose you could say, in an emotional way, that actually was more predictive then of poor well-being outcomes. So I suppose it suggests that when a lot of people seem to be doing well and happy, it can actually exacerbate for some people those feelings of low mood, because that felt pressure, they can't communicate well around that. They're expected to feel otherwise.
How does that manifest itself? Are they more likely to have mental health issues?
So our findings show they experience more negative emotion, less positive emotion, less satisfaction with life, more depression.
What could we do about this as a society, this pressure to feel happy?
I think firstly is to be a bit more aware of what we are pursuing and why, and what contributes to happiness, and realising that actually making happiness a goal is a little bit self-defeating and probably hollow if you think about it. And often happiness follows up from behind much more successfully than it does as a focal goal. I think the other is to recognise and be aware of the sort of channels that we're often influenced by socially. To recognise that, social media makes it look like everyone's having an amazing time and looking great on holiday and success and wins. But we need to remember that those same people are struggling at other points in their lives, maybe even those same points without revealing it. So we need to normalise the fact that we don't always feel that way, and it's actually normal not to, and it's not a problem, the fact we don't always feel like that. In fact, it's just what you expect. It's par for course for being a human. And perhaps focus a little less on just the positive emotionality, because again, yes, we know that it's a good indicator of flourishing, but it may be sending messages or, again, framing the value of emotion in a particular way for people. And it may be that really we should be focusing on other things that maybe lead a country to flourish and people to live well in that country, but not necessarily a focus on the positive emotionality aspect of it.
And if you could give a piece of advice to somebody who's listening to this and say, I feel that social pressure to feel happiness, what would you say to them?
Just recognise that it's probably not as real as it seems. Whilst it's out there, and it's often based on this sort of perception of how people respond and the social norms that we're surrounded by, sometimes it's actually worth breaking those a little bit. Someone needs to do it. Someone needs to take the first step. And, it's sometimes when you do break social norms and step out there, it's amazing how many people kind of going, oh, thank God someone said that. I feel exactly the same way. So, I think sometimes we've got to push through that a little bit and recognise that the idea that everyone around us is actually always in this happy, elated state, and that's the most valuable state for us to be in, is not really true. It's not really representative of our realities. And, being a bit brave sometimes and sharing the other side of it, I think, is actually really, really powerful and important, brings people together, creates connection, creates purpose for people as well, and in that sense leads to actually enhances our well-being too.
Just finally, what are you working on next? Where are you taking this data?
We're continuing to explore what leads to well-being. I'm quite interested in the idea that pursuing an ethical life can be both good for well-being but also bad for it, right? I mean, having to deal with the weightiness of thinking about where your coffee comes from and whether your eggs are sustainable and whether you've just used too much fossil fuel on the way to work can be quite a headache for people. And indeed, we're finding that can be a detriment to well-being. But then other aspects of pursuing the good life and pursuing those values, those moral values, seem to contribute and build well-being. So I think there's a whole really interesting connection there between what does it mean to be a good person and what does it mean to feel well.
Great. Well, thanks so much, Brock, for sharing your research with us. We appreciate it.
No worries, Gemma. Thank you.
Brock Bastian there. You can read more about his research on The Conversation, including a previous article he wrote about toxic positivity and what to do about it. We'll put a link to that in the show notes.
Elsewhere on The Conversation this week, we're covering, of course, the fast-evolving situation in Ukraine. Here's Eric Smalley with some recommended reading about the cyber dimensions of modern warfare.
Hello, this is Eric Smalley, technology editor for The Conversation, based in Boston. In covering the crisis in Ukraine, we've been looking at the role of information and disinformation in influencing events and shaping public perception. One question that looms large is whether Russian forces will stage a false flag attack as a pretext for invading Ukraine. We published an article by Scott Radnitz, an international studies scholar at the University of Washington, that gives a history of false flag attacks and addresses a more pertinent question. With satellite imagery and cell phone footage widely available on the internet, could Russia get away with an attempted false flag attack? Radnitz goes on to explain that the Russian government might not need to go through the costly and risky machinations of a true false flag attack to claim justification for invading Ukraine. Instead, Russia could craft a false narrative by tapping its history of blaming its targets for provoking a confrontation and its skill in waging disinformation campaigns. In a related story, we look at how technology has changed the nature of intelligence gathering and analysis. Craig Nazareth, a national intelligence expert at the University of Arizona, explains how low-cost satellites and drones and ubiquitous smartphones provide a wealth of raw intelligence data, how social media makes the data widely available, and how crowdsourcing and big data algorithms make it easier to analyze the data. Nazareth describes the concept of open-source intelligence. OSINT, as it's called, is intelligence data collected by private companies and individuals and made available on the internet. No government spies or top-secret technology involved. You can find these stories and all of our ongoing Ukraine coverage at theconversation.com.
Eric Smalley there in Boston.
That's it for this week. Thank you to all the academics who've spoken to us for this episode, and thanks to the Conversation editors Miriam Frankel, Noor Galani, Beth Daly and Martin LaMonica. And thanks to Alice Mason for our social media promotion and Katie Francis for help with our transcripts.
You can find us on Twitter at TC_audio, Instagram at theconversation.com, or email us, podcast@theconversation.com. You can also sign up for our free newsletter. Just click the link in the show notes. And if you're enjoying The Conversation Weekly, please leave a rating or review wherever your podcast apps allow you to do so.
The Conversation Weekly is co-produced by Mend Marawani and me, Gemma Ware, with sound design by Eloise Stevens. Our theme music is by Nita Sal.
I'm Dan Marino. Thank you for listening.